Welcome back. In this session, we'll continue with the discussion on harmonic oscillator. But this time, what we are going to do, we are going to add some friction. And we'll add some friction also to this mass. So if there is friction, for example, it's a high resistance, or you can say there is some resistance with the ground. So let's say now we include the friction. Now, if you take the friction into account, the response of this means the response of this system will be governed by the differential equation that looks like this. That looks like dx, sorry, mu v dx by dt plus kx 0. We are not still taking the input to this differential equation. We are saying this has some energy stored in this, and we are considering this frictional part. This is the frictional part that we have added to the system. And let's take the same condition that we took in the previous session, and let's suppose that this frictional constant is equal to 0.1. All right. So how do I solve this differential equation? Simulink. Now, before I solve this differential equation, Simulink, if you solve it analytically, remember the solution looks like this. Solution of this is simply e raised to minus b by 2m a cos omega naught t plus b sine omega naught t. B sine omega naught t. So this is the solution of this differential equation when we take friction into account. You can see now if I assume the same initial condition, it means x of 0 is 1 and x dash of 0 is 0. The response of this differential equation of this system becomes simply equal to e raised to minus b by m t cos omega naught t. When you add this term to it, you know this is damping. The cosine sub function will be now damping, means it will decrease. The amplitude of this cosine wave will decrease. So it will look like this. This will look like this. So this is cosine wave, so it will look like this. As time increases, the amplitude of this cosine wave decreases. All right. And to solve this in Simulink, what we can do, we can rearrange the terms here. We can say this is m. Let me use a different marker. This is m x double dash plus b x dash plus k x equal to 0. So I can write x dash on one side. This is x dash minus b by m dash minus k by m x. So this is how I arrange the terms. Then what we can do, we have now two terms on the right hand side. We can use a summer. First we obtain this and use a summer. In between, then we obtain x double dash. Now let me switch back to MATLAB to show you how we can do it. So this is our previous model. This is our previous model, and let me modify the same model. All right, let me modify this the same model. Let's do that. I need a summer, so I click on this and I will add a sum block, and you can see here is the sum block, and I need one more gain block. All right, I will use the same initial conditions. So this is minus b by m. So this is minus 0.1 divided by 2. I'm using the same mass value, and it shows you k here. Actually, it's not k, it is 0.1. And this is not x double dash, this is x double dash. And k is again equal to minus 500. I don't need to change this. So this is that differential equation that you have built in. X double dash is minus b by m times x dash. You can see x dash is here. It's as input to this gain block. That has a gain of minus b by m. Mine b is 0.1, m is 2. And let me change this. So then another input is minus k by m. K is 5 and m is 2, minus k by m, that's as input, and we get x double dash. Then we integrate this twice, we get x. So let me run it, show you the result. Let me run it and to display, show you the result. You can see the result. Now this may not be visible to you that it is damping. It is, although as time progresses, the value of this cosine wave decreases. But to visualize it better, let me increase the simulation time. Let me simply increase the simulation time to 30. So this is 10. Let me change it to 30 and run it again. So you can check indeed the cosine wave decreases. As time increases, the cosine wave decreases. You can change the simulation time to 100 and see the result. All right, let me end this session here. So this is when we added a frictional term to this. In the next session, what we'll do, we'll add an input to this oscillator. So if we add a force to this oscillator, that is changing the input. That means if we again and again change the location of this mass, how will the solution vary? All right, let me end it here.